Hello, this is Rahul. In this lecture, we will be learning routing information protocol. The routing information protocols uses the distance vector algorithms, and distance vector algorithms use the concept of Bellman-Ford algorithms. We'll see first the Bellman-Ford algorithm concept. Bellman-Ford algorithms use the concept of dynamic programming. In dynamic programming, what we do, if you have computed, suppose if you want to compute from R1 to R3 distance, but you have already computed R1 to R1 to R2, then you not need to compute again this much distance. Simply take the optimal one and find out the minimum of all these paths and add with this distance from R1 to R3 you can get very easily. If we write the formula, cost of reaching from R1 to R3, which will become cost of R1 to RT, which is already computed. This is, you can see, is the optimal one out of available paths from R1 to R1 to R2, right? Plus the minimum of all possible shortest paths from R2 to R3. As I told you, if you take some of these numbers, or some of these two, you get the cost of R1 to R3. So let's see how distance vector algorithms use the Bellman-Ford concept, and these concepts will help us to find out the least cost T, as we have seen in previous lecture. So we have a networks. In this networks we have 6 routers. You can see here 6 routers we have, and these routers are connected via links, and there are cost associated with each links, and initially each routers will have initially each router have their own vectors, initial vectors. What initial vector means, if suppose for corresponding to vectors R1 we have this vectors, right? What it means, suppose in the beginning from R1 to R4 there is a direct connections. From R1 to R2 there is a direct connection, and cost is 5 and 4. Similarly, we will write in initial vector corresponding to R1 to R4 is 4, R1 to R2 we will write 5, like this we will put, and rest of it we will put infinite. So this is the infinite because these routers are not directly connected. So initially we don't know. From R1 to R1, we are going from router to itself only. That's why we have put this as 0. Similarly, we can find out the initial vectors for router R2. Those routers who are connected with R2 directly will put some values. Rest of values we will put infinite because those routers are not directly connected. For sake of times, I have computed all the vectors and written over here. So this value is first 0 value is corresponding to R1, R2. You can see here we have a link from R1 to R2. So sorry, we can write here this would become 2. By mistake I have written this as 4, and no, this is not 2. R1 to R2 this would be 4, sorry, and from R1 to R4 the value is 5. This should be 5. I made a mistake, sorry for that, right? Similarly, other vectors we compute we prepare the initial vectors. Suppose R2 to R1 we have weight 4. We are talking about this one, and R2 to R3 we have a link, so that's why this value will come over here, and all other routers are not connected with R2, so that's why these value are infinite. Similarly, we will prepare initial vector for all other routers, right? So what if what how other the router suppose R1 want to transmit a packet from R6. R1 doesn't know whether R6 is connected with R1 via other routers. So what R1 will do, simply send a hello message to its neighbor, right? R1 sends hello message. In return, the R1's neighbors will sends its initial vectors to the R1. With the help of initial vectors, R1 will identify the adjacent neighbors connecting to these routers, because these routers are sending their own vectors to the R1 vectors, R1 routers. So let's see how R1 updates its vectors when R1 receives, suppose R1 is receiving vector of R4. R4 is a neighbor, you can see here. R4 is a neighbor of R1, right? Once R1's router received vectors of R4, how router R1 makes changes on its vector? Suppose the the vector at R1 is this one, and vector at R4 is this one. This vector is sent to the routers R1. Let's see what are the changes. Cost of R1 to R1, it cannot be minimized because it is already 0. This is 0, it is given. What if cost between R1 to R4, sorry, R1 to R2? So this is already given, this is 5. That's why we have written here 5, right? And this is a given in our vector of R1, right? From R1 to R2. Can we reach via R4 vector to R2 less than 5 cos? If it is possible, then you compute with R1 to R4 you go first, then R4 to R2 you go, right? Like this, R1 to R4 you go, then R4 to R2 you go, and compute the path. Suppose this one value I have written over here 5, and cost from R1 to R4, this is 4. This you can compute from here, this is 4, that's why it is written. Now R4 to R2, the cost is, you will look at the table or vector with R4 which is infinite, so that's why you will write here infinite. Then you take the minimum of these two values, you will get 5, right? I hope this is clear. Similarly, we will compute the cost to reach from R1 to R3, which is the minimum of infinite. This value is given, right? This value is given, so that's why I have written here infinite. Cost, can we reach to R3 via R4? This will tells us R1 to R4, this is 4. R4 to R3, can we reach? Yes, we can reach. This is 4. So 4 plus 4, it's become 8. If you take minimum of these two numbers, 8. Earlier it was infinity, and now it's become 8. Then we may make the change on our vectors of corresponding to router R. Similarly, we will compute for cost R1 to R4. The cost is given, which is 4. Can you minimize if you are going from R1 via R1 to R4 via R4? Actually you can't, because R4 to R4 is cost, this cost is 0, R1 to R4 that is given, so you will always get 4 same numbers. So similarly you compute for R1 to R5. R1 to R5, it is given in this vectors is infinitive. Cost of R1 to R4, the R1 to R4, this is 4, so that's why you write here 4. Cost of R4 to R5, R4 to R5, this is 1. 4 plus 1 you write here, and take minimum of these two numbers, you get 5, right? So for the last case, for this case we will look r1 to r6, we will compute the cost, you get infinity, so that's why there would not be any change. So once you get updations, you will keep update this one, and later on other routers will also send this router hello, then this router will return the its vector to its neighbors, right? This process continues until the vectors being changed. So similarly for the, if routers r2 is sending to r1's its vectors, then r2 makes change in its vectors, and this process continue until as I told you, the vectors vector is being changed corresponding to the routers. What are disadvantages with this routing protocols actually? First